Hello everyone, welcome to this tutorial of Intro to Pytorch. In this tutorial we'll go over the installation of Pytorch. I'll give you a brief overview of tensors, autograd, like autograd is a feature of Pytorch, and also we'll implement a very small neural network of our own. Like it is like the species prediction of iris flowers. So more about it later on. But it's very small, having only 150 data points. So it just to give a brief introduction of how is the overall framework of a neural network inside of PyTorch, so that we don't have we'll have easier understanding of the more complex models that will come on later on in the later tunes. First part is installing PyTorch. What how to install PyTorch so that you can use it on your device locally. One thing that you do, you have to have Python 3.8 and NumPy installed already. You have to satisfy those two requirements. Then first step is to go to this website that is over here. This will be the landing page. Just scroll down and go over here. This is where you'll select all the options that are there. I'll explain all the options in brief, and you'll get one command. This command you just have to run it in your command line interface, just copy paste, be it your terminal, be it your Windows PowerShell, or whatever that you have, and it will install PyTorch for you automatically. You don't have to do anything else. Coming to the PyTorch build, I'll suggest you to go to a stable one, because the preview will obviously be a bit unstable. It can behave in unexpected ways. That's why it's a preview and not the official release. I'll suggest you to go for the stable one. Then your OS. So depending on whatever OS that you have, you select one of these options: Linux, Mac, or Windows. So for me, this is Windows. So I'll be selecting Windows. And then the package that you'll use to install, if you're working in a Conda environment, then Conda, libtorch, or source, if you want to directly install from source, as you can see, this, if you select source, it just follow the instructions at the GitHub, or pip, I'll be using pip, so therefore it is pip. Then language, so is it CPP or Java or Python? So for this tutorial we'll be using Python, and even not only for this tutorial, but for the whole series we'll be using Python. So I'll suggest you to install Python only. But if you want to for some reason go into CPP or Java, you can try that out, but we'll be sticking to Python. So yeah. Then there is the compute platform. So as you famously know, neural networks are preferred to be computed over GPUs than CPUs, because GPUs are obviously way more faster than a CPU. We have the options of what compute platform do we have. So if you have CUDA, NVIDIA GPUs, then there is multiple versions, that is 11.8, 12.4. So depending on your version, you can select one. Mine is 12.4, that's why I selected CUDA 12.4. And for some reason, if you do not have a GPU inbuilt, you can do the CPU installation. The GPU installation includes the CPU version as well, but it's an addition that you can also run GPUs. I'll how to enable GPU computing, I'll show in the code demo that is coming after the installation. So depending on the options that you have selected, you'll get one command over here, and you just have to copy paste it into your terminal, and it will do the full installation for you. So yeah, that is it with the installation. It's a pretty straightforward and simple installation. We'll move on to the next part. Okay, so let us now verify this installation. Whatever we did, did it actually install PyTorch or not? Did it actually install the right CUDA package or not? So yeah, the first step is import torch, as you do any Python library, import numpy as np, import torch. If torch is not installed at all, this will throw an error. So that is that. And then torch.cuda is available. So since I have a GPU on my laptop locally, I can use this function and expect it to give out true in the ideal case, that yes, the GPU is available and PyTorch can access it because it has installed the right CUDA package. Now other two cases might be that you did a CUDA installation, but you do not have a GPU on a laptop. So torch.cuda is available will give false. Another case is you did the CUDA installation, you have a GPU, but your CUDA versions do not match. So then, and even in that case, it will come out to be false. In some cases, it might come out to be true if some dependencies work out. But in most of the cases, it ideally should return false. Let's run this cell. and see what happens. So yeah, like it got run successfully. So torch was imported and torch.CUDA turned out to be true. So yeah, all working good. Installation was perfect. So yeah, now coming to tensors. So like, what are tensors? Like, why are they so important, and why am I dedicating a section to it? As you know, like all of the computations in the neural networks are basically matrix multiplication. At its core, it's maths. It's straight up maths, matrix multiplication, linear algebra, and whatnot. A traditional way to do it is using NumPy arrays. But NumPy arrays sadly can only run on CPUs, so we cannot use the GPU's compute power to like run our neural network in a much faster way. And once we go to the bigger neural networks, they'll take days to run and train on data, and by chance if we run it on a CPU instead of a GPU, those days can be extended to weeks or even months in some cases. So therefore we cannot use the existing NumPy arrays, and therefore we have to define a new thing called as tensors. But to us humans, looking at data, tensors and NumPy arrays, you can call them the same. Like, they look the same. They just small variances, like, okay, like this tensor won't be printed outside of a NumPy array, and like if you print a NumPy array, probably you'll just get the square brackets, you won't get this format around. But like, it is a matrix at the end of the day. What it helps is, it helps the device to use the GPU's compute power to make the computations on the tensor. So that is all that you need to know. Not about how it does it. Let's not go over there. It does that, it helps, therefore we need tensors. So yeah, how to create one tensor? The first step is, okay, like tensors are all good and all, but how do we create one? So you can create a tensor from the raw data. So this is your data, 2 by 2 matrix of 1, 2, 3, 4, and then you just go torch.tensor and you pass the data, and you get whatever output that you get is the tensor that you have found. So as you can see, after printing it, we have printed it to be, and you get a printout. Otherwise, the second way is, you can pass a NumPy array as well. So you can first create a NumPy array, like this is a standard way. So np.array data, then torch.from NumPy, you pass the NumPy array and store that in another variable, and again, as you print, the output that you'll get is again a tensor, same thing. Another few initializations of tensors would be like, we do torch.once like something. So what it does is, it will create a tensor of only once, with having all the properties of x data. So x once is a tensor of all ones inside of it, having all the properties of x data. So whatever device that is on, which device, by what do I mean by device, we'll come back to that later. Whatever shape that is has, like it is 2 by 2, 2 by 3, 2 by 4, or 4 by 2, that, and a few other things that we do not need to go there right now. It will create of that way. So as you know, x data was of 2 by 2 shape. So the output that we get, like once tensor, is also of a 2 by 2 shape and is only filled with ones. Also the data type. So yeah, data type was integer over there, so the integer was copied on. Then we create a random. So like x torch.rand like. So x rand will be a tensor with the properties of x data, and it will be filled with random data. A property that is overwritten over here is the data type, which is torch.float data type. As we print a random tensor out, you can see that it is a 2 by 2 tensor with random integers in between. Like if I run it again, it should have the random tensor got changed. The random tensor got changed, as you can see. As you can see, the random tensor is always changing because it is initializing values randomly. And like how to print the shape of a tensor, you do xrand.shape and you'll get the shape as output. So how to define a tensor with a particular shape in mind. So let's say you want a tensor of shape 2 by 3 or 2 by 4 or something like that. How do you define that? So you will pass a tuple in this shape. Note that you have to leave this final dimension blank. That is the syntax of Pytorch, so we can't do anything about it really. And then you do torch.rand shape, torch.1 shape, torch.0 shape. So similarly, this is torch.rand random, torch.ones and torch.zeros. So yeah, another way of so that's printing it out. Another way of, like, this is again we are repeating it, like creating a tensor torch.rand of 3 by 4 shape. We want that, and printing the properties of this tensor. We get the shape of the tensor, which is tensor.shape, the data type of the tensor, which is tensor.dtype, and the device this tensor is on. So this is very important because like I told earlier that tensors enable us to use GPU computing, but to make use of that, we'll have to put a tensor on the GPU. Like by default, all that like after creation of all the tensors, they are stored on the CPU using the RAM of the machine. But to transfer them over to GPU, we'll have to do something specific. As you can see, it's like size is printed, data type is printed, and the default device is CPU. We'll have to transfer it to CUDA. Use this like CUDA as in like the GPU that we have, and this is the command to do it. And we'll block it with an if condition saying that if and only if torch.CUDA is available, you'll transfer it to CUDA. Like obviously, if we try to transfer it to CUDA without the CUDA being if the CUDA is unavailable and we want to transfer it to CUDA, it will throw an error. So since we do not want that, we'll do this. After doing this, once we do the same thing again, we'll get the device tensor stored on CUDA 0. So 0 is the index of the GPU. Since I only have one GPU, it will always return CUDA 0. But yeah, there is like, people might have multiple GPUs, so that's a whole different thing that's outside of the scope of this tutorial. So we won't go over there. Yeah, now we'll give a like that was tensors basically. Now we'll give a brief introduction about AutoGrad. So yeah, coming to AutoGrad now. So yeah, what is AutoGrad? Like why am I like introducing this in this tutorial? So like as we all know, like when we are training a neural network, like we do the loss propagation. Like loss is propagated backwards. Like what is loss? It is the like difference between the outputs of our model and the expected outputs, or the gold outputs, or like the true outputs, or whatever you want to call them. So yeah, like that loss has to propagate through every other parameter inside of the model, and every other parameter has to be adjusted according to that. So yeah, and again, like when the loss is back propagated, we need to compute the gradients, like by how much and in what direction do we have to shift the parameter by, and like off, like whatever it is. So yeah, so that is done by AutoGrad, and like AutoGrad is it has a built-in differentiation engine called torch.AutoGrad. It supports automatic computation of gradient for any computational graph. What is a computational graph? I'll show that to you soon. But yeah, first let's like to visualize it better and to understand it better. Let's implement a like basic neural network. I won't even call it a neural network, a basic model, like one equation basically. Yeah. So yeah, like x is equal to torch.1's phi is the input tensor, y is the output tensor, w is this can be w is the weight, and b is the bias that is introduced, and the equation of the model would be output equals x times w plus b, and then we calculate the loss against this our output that we have got from the model versus the expected output of the model. So yeah, and then so the gradient computation, like to tell Torch that okay, we need gradient computation for this particular parameters, like w and b will be the parameters of the model. We have to set requires grad equal to true, and this can be set later as well with just like whatever it else name is dot requires grad bracket true. So this can be set later as well. It's not that you have to set it right now or something like that. Yeah, so the code that you have set up defines this computational graph. So x is there, it gets multiplied with w, then the bias gets added, then we get z, and then a cross entropy loss is calculated against y. So this is the most basic computational graph that you'll have. Obviously, the computational graphs of like models later on that we'll do will be much more complicated than this, but yeah, this is one so that we can easily understand. And in this network, as you can see, like as I stated earlier as well, w and b are the parameters which you need to optimize so that the output that we get is like very near to y. Thus, we need to be able to compute the gradients of loss functions with respect to these variables. In order to do that, we set the required grad property of true. So yeah, like fine, like all this is done. We need to do this, but how to actually do it in code? It's just one line, loss dot backward. So yeah, like that is why Pytorch is also good, easy like to implement neural networks and all that. So like yeah, it just like loss propagation is just loss dot backwards. That's it. And yeah, like two more lines we have to add later on. Like I'll explain it later on when we have the short demo of the neural network that is there. Anyways, yeah, so by default, all the tensors with require grads is equal to true are tracking their computation history and support the gradient computation. However, in some cases, we do not want that to happen. Like, what are these cases? Like I mean, like there might be some cases in which we do not want this, like these gradients to be computed. What would those cases be? One of the cases that I can think of two right now, but one of the cases would be when we are doing a forward pass, we are just doing inference on the model. We like after the model has been trained, we are just doing inference at testing time, and we do not need to compute these gradients because we are not gonna propagate our loss backwards. So yeah, that is one thing where we do not need these. Another thing would be when we like okay, so let's say for some reason we have to there is a set of two parameters, parameter a. Oh, okay, like even while LoRa fine tuning, in LoRa fine tuning, what we do is this will might be explored later on as well. What we do is we like freeze the parameters of the model and then apply an adapter on top, and we only tune the parameters of the adapter. More on this later, but how do we freeze the parameters? Like since we have to freeze these parameters, there has to be a way in it. Or for some reason, we'll say we have a set of two parameters, parameter A and parameter B, and for like half the number of epochs or the time frame in which the model is training, I only want to tune parameters A, and in the second half, I only want to tune parameter B. So we have to have a mechanism to freeze them. So yeah, so that is and but we can't have requires grad as false for both or true for both. So we'll have a computation, like whatever the computation code is, we'll have to set a block on it, which is torch.nograd. So let's say we are doing inference over here, z is equal to torch.matml x comma w plus b. We are doing inference at this point and we don't want the gradients to calculate it. We'll just say with torch.nograd, you'll calculate this, and yeah, that will go ahead with that. So as you can see, without doing that, if we do print the property requires grad, then we'll first get true, and if we do it with the block, we'll get false. So yeah, that is the straightforward reason. So yeah, like to mark some parameters in a neural network as frozen parameters, or to speed up computations when you're only doing the forward pass, like at inference time, there's computation on tensors who do not track gradients would be more efficient. Like yeah, these are the reasons. So yeah, what is the real advantage of Pytorch over TensorFlow? Like I'm sure many of you would have this question, like why aren't we doing TensorFlow? Why are we doing Pytorch? Or if you might not have, like it's fine, no issues completely. But yeah, so these computational graphs that I showed you earlier are dynamic in Pytorch. So like the important thing to note over here is that the graph that is recreated from scratch every time. So after doing each dot backward call, the whole graph is reconstructed at the when the computation starts again. So after each dot backward call, AutoGrad starts populating a new graph. This is exactly what allows us to use control flow statements in our model, like if else. So if we are coding in TensorFlow, like we'll the newer versions of TensorFlow have this, but PyTorch does it better. So yeah, we can, and it's easier to implement in PyTorch as well. So we can just write if else statements key, like okay, if epoch number is greater than 50, then follow this line of code. If epoch number is less than 50, follow this line of code. So we can do that much easily in PyTorch, and there are some use cases where you might need to do this. So yeah, and in general, even PyTorch is more Pythonic than TensorFlow is. Like it is much more readable and it does not divert much away from the syntax of Python itself. So yeah, And we can also change the shape, size, and operations at every iteration of epochs if we need it. That is the case. So yeah, that's the major advantage Pytorch has over TensorFlow. Yeah, so let's come to building a model, like a very basic one, but yeah, let's build an actual model. So yeah, let's start building a model now. Yeah, like again, it's a very basic one, like with only 150 data points and like 4 inputs and a 3-way classification. So yeah, so the inputs to the model would be our sepal length, sepal width, petal width, and like the yeah. So the species are initially in this like sentence, like it's a string format. So like you can see this iris setosa, iris versicolor, and iris virginica. So yeah, we'll like first convert these into numeric data, and we'll have yeah, like those stored in X data and Y data. And as you can see, all the sepal length, width, and petal length and width is all numeric only, like in float data type. So yeah, so this is basic data conversion. Like we'll have to do it. So the X data shape is 150, 4, and Y data shape is 150. So Y essentially contains the printout, like it contains the classes. So I'll print Y data as well. As you can see, it contains all the classes, so 0, 1, and 2, and X data will contain all the tensors, basically like 150 tensors in the row and 4 of, like, whatever the corresponding categories are. So the categories in this would be sepal length, width, petal length, and petal width. So yeah, that is how it is constructed right now. Yeah, then coming to the, like, as we know, we have to split our data into train and test. Again, like not using the validation set here because it's a very small data set. Like so yeah, just for demonstration purposes, I'm not splitting it into validation part. But yeah, like it's a predefined library in sklearn. Like yeah, doing the like test data side is point to like random state, so that we get always we get a deterministic data. So yeah, that is there. Then there comes the final model, like model definition. Like how do we define this model? What are the computations that goes inside of it? How does the output come? How is the loss calculated? And all of that. Yeah. So yeah, so we define a class for our model. It inherits from the nn.module class. Then we have two functions over here. One is init. This is the function that is called when the class is defined, like an object is made, as you can see over here, and all these variables are defined. So yeah, this is again like this, like you can call, like you can take this as syntax. So like you have to do it every time you define a class of an module, every time you want to define a neural network. So yeah, you can take this off as syntax. Then comes the first fully connected layer, which is a like, so we had, if you remember, on top we are imported torch dot oh sorry, my bad, it's not on that on top. Like we had imported torch over here as torch.nn as nn. So yeah, the nn module inside of the Python library torch, there is sits all the layers of neural networks, so linear, sequential, and all that. I'll show you more layers later on when we do other bigger code demos. But right now we are just like, as a basic model, we just need a few linear layers. So yeah, so the first fully connected layer is a linear layer, like nn.linear, with 4 input points and 16 output points. So, and now since we are constructing a whole neural network, so 16 will be the hidden layer that the network will have. So, and then the second one is also another fully connected layer with linear layer with 16 to 8. So 16 input neurons go to 8 neurons in the next layer, and then finally those 8 go to 3. And then we also define an activation function, nn.release. So nn also in addition to all the layers of neural networks, we also have all the activation functions. We do, and all the losses as well, as we can like see it later. We will set the ReLU as nn.ReLU. So yeah. Now comes the forward pass of the model. So like, how will the model calculate all, like take inputs, do some calculation, and give the output? How will the model do that? This is defined in the forward pass. So whenever you pass an input to this model, this object model that is there, it'll go to this function. It'll go to this forward function, and then this is where the input will come, and that will start getting calculated. So the first call is through the FC1, that is fully connected layer 1, 4 to 16, and then an activation function is like called on top of it, and thing is stored again in X. So like I can call this as X1 for simplicity, for you to understand. Then that same X1 is passed on to the FC2, and then is passed to an activation function, and then that is stored in X3. Then that same X3 is passed on to FC3 and stored in X4, and we return the X4, that is the output of the model. So now what will happen is we'll receive a 4-dimensional input that will get passed on to 16 dimensions once we pass to FC1. Then that 16 dimensions will be passed on to 8 dimensions, and when we pass to FC2, and those 8 dimensions will be collapsed to 3 dimensions, which is for 3 species, like 3 classes, 3 species, therefore 3 at the end. So yeah, that is how this basic layer is converted. And one thing that you can notice over here is that we do not have a ReLU function on the last layer. Like there's no activation on the output layer, as we are using cross entropy loss, and like cross entropy loss is generally used for classification tasks, as you might already know. And cross entropy loss already does have some activation functions inbuilt into it, which is softmax, if I'm not wrong. You can go to the Python documentation to read more about it. So yeah, we'll provide the link for that as well, but you can do a basic Google search for that. And then there is an optimizer. So as you can see, stochastic gradient descent is an optimizer. So we need that as well. How to after calculating the loss, how are we propagating it? How are we tuning our parameters? That is done by the optimizer. So that as we had imported torch.optim as optim, we have all these optimizers residing in the optim torch.optim module, and we are using Atom Optimizer over here because Atom Optimizer is generally better than HJD. So yeah, we'll use Atom Optimizer again. We'll not go in how it is working, but we'll straight up use it. We'll say that okay, all the parameters of the model are to be optimized, and okay, so the linear layers will have parameters of their own. So as you're going from 4 neurons to 16 neurons, there is a weight matrix between the layer, that is the parameter. So that is handled by Pytorch by itself. Therefore, it is it comes out to be more Pythonic in itself. So yeah, so therefore we'll pass the entire parameters of the model, and then we'll pass the learning rate as LR. For right now it is 0.01. Again, I'm reiterating it, we only have 150 data points, so we really do not need to think this much. Neural network is probably overkill for this data set, but yeah. Then comes the training loop. So how do you finally train a neural network? You have to find it, you have to find what the loss is, how to optimize it. Now how do you actually train it? So yeah, comes the training loop part of it now. So we'll run this for 50 epochs. So for epoch and range epoch is Python code, basic Python code. Yeah. So for each epochs, we'll pass the entire training data set. So one thing about Pytorch is it expects batched output. So what are batches and how to deal with that, we'll go into that in the next tutorial about LSTMs, I believe. But for now, assume that you have you have only one batch, and one batch has 150 inputs inside of it, which is the entire data set, and it is being passed to the model. With each epoch, this whole thing is done. So X-train data set, that is the entire training part of it. Since we have done 20% to test, so 80% of 150 that will be inside of this is passed to the model. All the computations are done. So right now 80% of 150 is the batch size, 4, which is our input dimension. That is the shape of this X-train that is passed to the model, and that is what even the model is expecting. So it's just in case if you do not want to give batch input, you'll have to specify batch dimension as 1, and you'll have to add 1 comma whatever your input is, so that it is easier for the model to understand. So that is how Pytorch works. So basically that. So yeah, then you'll get the output, then you'll pass it to the criterion, you'll get output, and against the true y train is the expected output, is the gold output. You'll calculate the loss through the criterion. As you can see, it is cross entropy loss. You'll store the loss, and then you'll do loss sort backward. But before that, you're doing optimizer.0grad and optimizer, and after that, you're doing optimizer.step. So what are these two things? You had not introduced this earlier. What are these two things? So yeah, while calculating loss, Pytorch by default accumulates gradients from all the batches. So like all the epochs, rather I should say. So when we are calculating those like epochs over here, as we are saying, because like we have not yet we are passing the entire data set as a batch, so there is no real concept of a batch. We'll get to that later. So it's a more complicated task. I'll explain that later. But so I'll rather change it over here from all epochs. Yeah. So Pytorch by default will start accumulating all gradients by default throughout all the epochs. So for that, we'll have to reset these epochs. So like basically, once we are the loss of that, will calculates the gradients, right? So like for them to prevent the accumulation of this into one particular area. And like doing miscalculations of how the parameters are supposed to be tuned, we'll have to reset the gradients at every point. So therefore we do optimizer.0grad before we actually calculate the gradients. So yeah, after doing optimizer.0grad, we do loss.backwards, and then we do optimizer.step. What does optimizer.step do? It actually updates the parameters. So loss.backwards only calculates the gradients, and optimizer.step updates the model's parameters according to the calculated gradients. And then then we're just printing the loss for every 10 epochs. So like as you can see, the loss is going down, which is what we want to see. Then comes the testing loop. Okay, now we have trained the model. How do I test it? Like how well is the model working? How do I test it actually? So yeah. Again, like model, first we set the model into eval position, and then with torch.nograd, which is both of these are like to save the not compute the gradients and all that, it's for that, not calculate the gradients and store all the computations necessary to make it more efficient, to make a forward pass, to make inference much more efficient. These two things have to be done. So yeah, then we pass the test data set now. So now we have done the training on a trained data set. We pick up the test data set and pass it through the model. We get the output, and then we compare it against the test output. So torch.max is also a function. So again, we are doing a three-way classification, right? So species 1, species 2, species 3. So the model is assigning probabilities to the three species that we have found. So whatever the max probability is, that is what essentially this model is predicting it to be. So we'll do torch.max along our outputs along the dimension 1. So what is happening over here is, so dimension 1, as in there is dimension 0 and dimension 1. Dimension 0 is the batches, which is 20% of 150 in our case, and dimension 1 is the actual prediction, that is the prediction throughout the classes. So therefore we are picking the max along those sides, and then we are getting two outputs. One is an underscore, which is implying that we are not going to use it, and one is the predicted. So the two outputs that torch.max usually gives is this is the value of the maximum. So let's say species 2 has the highest probability with 0.6. Then over here 0.6 will be stored, and in predicted the index of that class will be stored. So as you can recall, our y test or y data or y train was actually the indices of the class. So we require the indices and not the probability. So therefore we'll only have the indices and define the probabilities as underscore, saying that okay, we are not going to use it anymore. As you can see, after we print the predicted variables, you can see that only the classes are there. So this is the prediction of our model. And then accuracy is a simple calculation over the y-test, how many of them, if they match, add them, and then divide it over the total size, and then print the accuracy by multiplying it by 100. Yeah, pretty straightforward. So yeah, that is our test loop. This is how a basic neural network will run, and that is it for the tutorial. We'll going into the future tutorials, we'll have much more complicated models, which will go over. I'll make sure to also explain them in depth as well. So yeah, see you in the next tutorial.